In the span of just 5 months, two brand new Boeing 737 MAX 8 aircraft plunged from the sky, claiming 346 lives. First, Lion Air Flight 610 in October 2018, followed by Ethiopian Airlines Flight 302 in March 2019. These identical tragedies shocked the world and shattered Boeing's century-old reputation for safety. Initial investigations quickly pointed to a systemic issue, not isolated mechanical failures or pilot error. The question wasn't if something was wrong, but what exactly, and why it wasn't caught sooner. This deep dive will uncover the layers of decisions that led to these catastrophic events. To understand the crashes, we must first understand the 737 MAX itself. Boeing launched the MAX in response to Airbus's highly successful A320neo, a fuel-efficient upgrade of their popular single-aisle jet. Boeing needed to compete, and fast. The 737 MAX was essentially a re-engined version of the decades-old 737 airframe, fitted with larger, more powerful, and fuel-efficient engines. These new engines, however, were mounted further forward and higher on the wing, which subtly altered the aircraft's aerodynamic characteristics. This seemingly minor change would have profound, fatal consequences. Boeing's choice to modify an existing design, rather than create a wholly new aircraft, stemmed from a desire to save time and money. Crucially, it also meant airlines could certify pilots on the MAX quickly, without requiring costly and extensive simulator training, a major selling point. But the larger engines, being more forward, created an aerodynamic tendency for the nose to pitch up in certain flight conditions. This was a critical divergence from previous 737 models. Boeing engineers had to compensate for this new characteristic, leading to the development of a complex automated system. The solution Boeing devised was the Maneuvering Characteristics Augmentation System, or MCAS. This software system was designed to automatically push the aircraft's nose down if it detected a high angle of attack, preventing a stall. It was a background system, meant to be invisible to pilots, only activating in specific, rare flight regimes. Crucially, MCAS was designed to operate based on data from a single angle of attack sensor, without cross-referencing with a second sensor. This single point of failure proved to be a catastrophic design choice, laying the groundwork for disaster. Both crashes followed an eerily similar pattern: a faulty angle of attack (AOA) sensor began transmitting erroneous data, indicating the aircraft's nose was dangerously high when it was not. This false input triggered MCAS. Because MCAS was designed to use only one AOA sensor and operate without redundancy, it repeatedly commanded the nose down, despite pilots' desperate attempts to pull it up. The pilots were effectively fighting against an invisible, relentless adversary. It was a software system overriding human control, driven by bad data. Perhaps the most shocking revelation was the extent of pilot unawareness. Many pilots flying the 737 MAX had never even heard of MCAS, let alone understood its potential behavior. Boeing, in its efforts to market the MAX as an easy transition from older 737 models, minimized documentation about the new system. This meant airlines could avoid costly full-motion simulator training, a significant incentive. Consequently, when MCAS malfunctioned, pilots lacked the knowledge and training to recognize what was happening or how to effectively counter it. Central to the crisis was the role of the Federal Aviation Administration, the FAA. For decades, the FAA has delegated significant portions of its certification process to the aircraft manufacturers themselves, a system known as Organization Designation Authorization, or ODA. This allowed Boeing employees, acting as FAA representatives, to sign off on safety-critical aspects of the 737 MAX. Critics argue this created an inherent conflict of interest, prioritizing production schedules over thorough safety scrutiny. The result was an oversight process that missed critical design flaws like the single-sensor MCAS. Boeing was under immense pressure to respond to Airbus. The A320neo was selling rapidly, threatening Boeing's market dominance in the lucrative single-aisle segment. This urgency, arguably, contributed to design shortcuts and a compressed development timeline for the 737 MAX, speed to market, minimizing training costs for airlines, and leveraging the existing 737 certification path became paramount. This commercial imperative overshadowed, or at least compromised, the rigorous safety-first culture Boeing was once known for. The consequences were devastating, highlighting the dangers of unchecked corporate ambition. Let's compare the traditional approach to flight controls with the MAX's reliance on automation. Older aircraft typically provided clear manual overrides for most systems. The 737 MAX MCOS, however, was designed to function in the background, without immediate pilot input or detailed notification. This design philosophy created a significant disconnect. Pilots were trained to handle runaway trim, but not a system that aggressively commanded nose-down movements based on flawed data, without their explicit knowledge or control. It was a fight against an unknown enemy. Following the second crash in March 2019, global pressure mounted rapidly. Regulators worldwide, initially led by China, grounded the entire 737 MAX fleet. The FAA, initially hesitant, eventually followed suit. This unprecedented move idled thousands of aircraft and cost Boeing billions. It was a public acknowledgement of the profound safety crisis. The grounding was a necessary step, providing time for investigations, software fixes, and a complete re-evaluation of the aircraft's design and certification process. The reputational damage to Boeing was immense, and trust in aviation safety was severely shaken. Boeing's primary response was a comprehensive software update for MCOS. The updated system now takes input from both AOA sensors, comparing them to ensure consistency. If there's a significant discrepancy, MCOS is deactivated. Furthermore, MCOS will only activate once per event, preventing the repeated nose-down commands that plagued the original system. Pilots also received enhanced training and detailed documentation. This software patch was crucial, but it highlighted how a seemingly small software design choice, combined with a lack of redundancy, could have such catastrophic real-world consequences. The human cost of the 737 MAX crashes is immeasurable. 346 lives abruptly ended, leaving behind grieving families. The financial impact on Boeing was staggering. Estimates place direct costs, including compensation to airlines, fines, and production disruptions, in the tens of billions of dollars. Boeing's market capitalization plunged, and its reputation took a severe hit. Beyond the immediate losses, the crisis eroded public trust in aviation safety, prompting calls for more rigorous independent oversight and a re-evaluation of the FAA's certification practices. The crisis also triggered extensive investigations by the U.S. Congress. Numerous hearings brought Boeing executives and FAA officials to testify, often revealing systemic failures. Congressional reports sharply criticized both Boeing for its culture of concealment and the FAA for its lax oversight. Recommendations included significant reforms to the ODA program, increased funding for the FAA, and stricter requirements for new aircraft certification. These investigations underscored that the problem wasn't just a technical glitch, but a failure of corporate governance and regulatory effectiveness. After 20 months, the 737 MAX was cleared to fly again in late 2020 by the FAA, followed by other global regulators. This ungrounding came with stringent conditions, including mandatory software updates, additional pilot training, and detailed pre-flight checks. While airlines are slowly reintroducing the aircraft into service, the shadow of the crashes remains. Restoring public trust in the 737 MAX and, more broadly, in Boeing's commitment to safety, is a long-term challenge. It requires transparency, consistent vigilance, and a fundamental shift in priorities for the aerospace giant. The Boeing 737 MAX saga is a stark reminder of the complex interplay between engineering, economics, and regulation. It teaches us that shortcuts in design, driven by market pressure, can have deadly consequences. It highlights the dangers of inadequate pilot training for complex automated systems. And it exposes the vulnerabilities of a regulatory system that relies too heavily on the very entities it is meant to oversee. The hope is that these lessons will lead to lasting reforms, ensuring that the pursuit of profit never again compromises the fundamental principle of aviation, safety above all else. This crisis has forced a comparison between the FAA's ODA model and more centralized regulatory approaches. While the ODA system aims for efficiency, its critics argue it compromises independence. Other global regulators, like EASA in Europe, maintain a more direct oversight model, particularly for critical systems. The 737 MAX failures underscore the debate: how much authority should be delegated to manufacturers, and at what point does efficiency become a liability? Future aircraft certifications may see a significant shift towards more direct and independent scrutiny, globally. Boeing is now at a critical juncture. The company faces immense pressure to regain its reputation, deliver on existing orders, and innovate responsibly. While the 737 MAX is flying again, the incidents have prompted a deep internal reflection on its engineering culture and safety processes. Future aircraft development, like its potential new mid-market airplane, will undoubtedly be scrutinized with far greater intensity by both regulators and the public. The real reason for the crashes serves as a permanent cautionary tale, shaping the future of aviation safety for decades to come.